had a break. You didn't work the whole time on school or work or life. Okay. But it is the last unit of class, all right? Your exam grades are on Blackboard. You're welcome to check them out. You'll get your exam back on Thursday. Later this afternoon, the answer key will probably pop up, so you can take a look at that. You might be able to recognize right off that you missed a couple minutes. I had one question that, like, uniformly everybody got wrong, and so I was like, well, that's a bad question. Okay, so check that one out. So instead of being out of 90 points, everybody's grade is out of 89. If you happen to get that question right, honestly, by chance, I think, then well, you got an extra bonus point. Okay. Yeah. All right. We're starting into our last unit of class, of course, and so we're going to be focusing on air and the atmosphere for this last 5 weeks or so of class. We talked about water, we talked about land, our energy non-renewable resources that we lightly started talking about at the end of class the Tuesday before our exam at spring break. Definitely bleed over into this idea of air pollution. And so we're going to start by discussing renewable and non-renewable energy resources in a bit of detail. We'll spend a week talking about different types of air pollution, and then we're going to end the semester talking about climate change and climate change consequences. The last couple classes are a little bit flexing in terms of what's going to happen in the last week of class. I definitely have a few topics that I want us to touch on, but depending upon how much of a conversation we want to have about these other 3 topics that are really important as well, we'll take material out and reshape material there in the last week of class. Okay, so that's where we're going. We had a service learning project over spring break, which was totally fun, I thought. And we went out to the Cincinnati Nature Center, the Long Branch Farm, and we cut down invasive winter creeper, I think it was called. And the winter creeper is this invasive vine from our region. It's from Asia, I think from China in particular. Olivia, our Cincinnati nature person, said, and it climbs up trees and then it strangles them. And so it remains leafy and somewhat green over winter time. And so that made it really easy to see in the trees, which are totally lashing all over right now. And so we went around the different trees, sniffing off the vines at the bottom, taking out chunks, and Olivia would spray them with Roundup. And sure enough, when I got home and I looked at my trees in my yard, I was like, oh my God, there it is. I ran over, put the vines, made sure I had done that before. And kind of felt like I had it a little bit under control. The other thing that, of course, I was doing when I was out there was I was pulling up little baby honeysuckle plants and another invasive species, and sure enough, when I got home, I was like, oh my gosh, I had a whole bunch of honeysuckle in my yard that I had to pull out. So definitely, it was a tree-saving expedition. Our next service learning opportunity will be April 13th, and we're going to participate in the Claremont County Litter Cleanup, and so I will pick a site for us to do that Saturday morning. That comes up, I guess, about 3 weeks from now. If you have not already done a service learning opportunity, you need to come to the third one. And if you cannot come on the 13th, please let me know, and I will help you connect with an organization that you can volunteer with in the next couple of weeks. Okay? This is important because your homework 4 is tied to your service learning experience. In order to be able to do homework 4, you need to complete one. Those of you who just participated in Service Learning Project 2, your homework 4 is due next Tuesday, April 2nd. I want you to take like a week, and most of the week and a half to think about it, and then write about it and get it done. Don't wait till the end of the semester. Okay? This is also important because your homework 6, which is upcoming in the next couple of weeks, is also going to be based on your Service Learning Project. I'm going to ask you to come up with an idea of something that you can do in association with this organization. It's either related to what you did or that you noticed that they had about stuff. And so you need to participate in something in order to be able to do this 10 points worth. And again, if you're having trouble finding one, please don't hesitate to let me know. I'm more than happy to connect you with one of the organizations we've already worked at or with the other resources. It was fun. Dominic and Elena and Lexi and Grace had a good time. We met some people for making it basically. Okay. All right, guys. Our learning objectives for today are to continue talking about energy resources and energy efficiency. And we're going to start out by reminding ourselves what our non-renewable energy resources are. And then we're going to talk about the 3 ways that we can evaluate them in order to determine whether or not this is an actual useful energy resource. And so We're going to look at net energy and energy return on investment. We're going to look at energy density, how much energy is kind of given off, and in the first place, how much energy is there to get. And then we're going to look at what I call sustainability. And this is kind of the pros and the cons, what's good and what's bad about our fossil fuel energy resources. And throughout this, I want you to be thinking about, what do we use this energy for? What can we replace this energy use with? Particularly when we consider that our electricity and transportation is based on one of these four fossil fuel resources to a great extent. And so today we're going to be really focused on petroleum or oil products, natural gas, coal, and nuclear energy. Okay, where we left off talking about these different resources the week before spring break was an understanding that we had a bunch of different energy resources. For the most part, here in the United States, 90% of our energy comes from one of these non-renewable energy resources. Coal, petroleum, natural gas, or nuclear. Only 10% of our current mix in the United States is really what we consider a renewable energy resource. Okay, solar, wind, hydro, geothermal, kinetic energy of a whole bunch of different types that we can think of. There are some small-scale biomass burners that are happening as well that kind of contribute to this process. There are all kinds of really interesting ideas for renewable energy resources, but only a few of them have kind of made it to the big league scale of our fossil fuel industry. What I also want you to recognize is that how we utilize these energy resources is a little bit different depending upon the particular resource. So a lot of our coal and a lot of our natural gas goes into electricity generation. Okay? But a lot of our petroleum products goes into transportation energy. Okay? We don't really burn coal in cars, right? Okay, that's mostly an energy, electricity resource. We're going to be focused on electricity generation today, and that I think gives us a kind of a better understanding of the physics of energy production and why some of these particular products are particularly bad. Recognize that where we most often interact with these fossil fuels is in transportation, when we're pumping gas into our car and then we're utilizing it. Some of us may use natural gas every day in our cooking process, and so if you see the flame, you know that you're using it. But our electricity generation just kind of happens. You turn on the lights, and it goes to work. And we don't think about how that electricity is actually produced. And so that's what we want to get a better understanding of today. But first, we're going to do our in-class activities for today. Would you like yellow, blue, or green? I have somebody else that can. Yellow, blue, or green. All right, write your name on the back of your slip. This is your in-class activity today. Write your name on your slip.
Oh,
Did you get two, Ethan? That's okay. Just turn one in. You can bring them both up to the front when it's your turn, but write your name on one of them. Okay. What I want to kind of start and bring home at the beginning of class today, as well as give you something to eat while we start talking about slides, right, is why non-renewable resources are particularly concerning. And again, we've talked about non-renewable mineral resources, and we know if we run out, and we're left, they get more expensive. We know when they get scarce, they get more expensive. We don't really think about running out of fossil fuels because we actually have a lot of them. But we don't have a lot of processed or manufactured, ready-to-use fossil fuel resources. There's this whole process that goes into getting them out of the ground and getting them available to us. Oh, it sounds good. Okay. And for each generation of humans, you can think of yourselves as users of this particular resource, and our resource right now is popcorn. You have access to it in a fashion that's related to other generations, particularly the generations that have come before you, and it's harder for us to envision how our actions impact the generations that come after us. So the way this works is that when I call your generation, we're going to start with first. You can come up and you can take as much popcorn as you like from the back. Okay, you can take that. All right, if you are a first generation person, bring your slip up and come get some popcorn.
I can't believe I'm sitting in the hall. First day back from school, but thinking class started at 11:20.
Oh, that's good. Yeah. And again, here, I'll take your slip.
so confused why.
You can take 2 handfuls, you can take as much popcorn as you can. Okay, if you
Just
are
a
a
little.
second generation person, come get some popcorn. Okay, if you are a third generation person, you can come get some popcorn. Okay, if you are a fourth generation green slip, it's your turn. Oh boy. Oh boy. Take as much popcorn as you want. Yes.
You may not
Well,
walk
and
out with
Willow
the bag.
first.
Wait, okay, hold on, Willow, I got you.
Are you serious? Did we not see that coming?
You can do that. You
We
can
totally
do
saw.
that.
Don't get it by face.
I totally saw it coming, that's why I was like,
I could see that happen a mile
What you
away.
said, we can take as much as we want.
Yeah, that was,
All right.
that's when we
Okay, did I
knew.
get everybody's slip?
That was a co-op you just operated, you shared with your neighbors.
It was kind of nice. It was good that Andrew got fourth generation at least.
Yeah.
I'm just imagining he got first.
Okay, there were 2 first generation slips, and there were 2 second generation slips. And I think there were 4 third generation. And then there were probably 8 people in that fourth generation. And what happened?
Somebody wanted to take it all.
It ran out, right? There were a couple that were have more popcorn.
I just took a small handful. I took it
We
first.
ran out, right? We didn't have enough popcorn for everybody in the class to have some. Even though Andrew shared a little bit with other people.
Whoa.
Was it Ethan and Grace, you guys missed out? No, you did not have the whole second bag. Okay, so we have this increasing population of users, just like we have an increasing human population on the planet. And we have this non-renewable resource. There's only so much popcorn to be had in the bag. And sure enough, when we got to the fourth generation, it ran out. There wasn't enough. What's going to happen to the next generation? It's not like there's not going to be more people on the planet.
We're not going to need to start with.
There's not even any to start with, right? Willow? Yeah, okay.
Yeah.
What happened to the quality of the popcorn as you got to the end of the bag? Like, Andrew, what's at the bottom of the bag here?
it's pretty good, actually.
It wasn't as good or intact.
Yeah, you get crumbs, right, as you get down to the little pieces of popcorn that are left at the end. So the quality of the resource declines. It's harder to get the same amount of usefulness out of the little bits, even though you could probably weigh it and you could get an equivalent amount as you move through the class. This is what happens to our non-renewable resources. If everybody takes as much as they want, it runs out. There's not enough left. It's unsustainable use. And so what I want you to constantly be thinking about with our energy resources is that for non-renewable fossil fuel energy resources that it takes hundreds of millions of years to produce in the first place, we are using them at a rate faster than they can be replenished. Okay? Eventually they will run out. Okay? Many generations of humans in the future, if we continue at our current use rate, they will eventually run out. And that's concerning. That means that there are things that we can do now, not only switching to renewable energy resources, but in terms of energy efficiency today, that are really important for conserving this resource. Okay? That's first and foremost. We want this resource to be available for future generations. There are lots of other reasons as well, but we want to turn from non-renewable fossil fuels towards renewable energy resources. Are you sure you don't? All right. All right, so we get it. So, as I mentioned, you'll share it. He'll sell it, yeah. Dude, my kid totally did that on the bus the other day. He was like, I had this thing that this other kid wanted, so I sold it to him for money. And I was like, all right.
That works. Enterprising young man.
be evaluating our energy resources on. And we're going to use these same three standards for our non-renewable and our renewable energy resources. So first we're going to talk about energy density, and then we're going to talk about efficiency, which is that net energy return on investment. And then we're going to talk about sustainability for these guys. Okay? Our understanding of energy density, let's just talk a little bit about two of the laws of thermodynamics, which can sound a little off-putting at the start, but it really comes down to these two lines that are in red on the graph. Okay? And in our energy production, whether it's electricity or for transportation or heating and cooking purposes, we always have to follow the first law of thermodynamics, which affects energy density, how much energy is available from a given energy resource. And the first law of thermodynamics is the law of conservation of energy. And this states very simply that when you finish a reaction, you will have as much energy at the end as you started with. But just like we cannot create and destroy matter, we cannot create and destroy energy. We can transform it. We can turn it from one type of energy into another, but we will only have at the end what we started with. You cannot get more out than what you put into the system. When we create electricity using fossil fuels, and even when we do nuclear energy, we do a very similar process regardless of the starting material. So what we have shown here is a diagram of how we produce electricity when we start with coal. And this is all about the law of conservation of energy, and that we're going to be putting chemical energy stored in the carbon, hydrogen, oxygen bonds in coal and we're going to get electrical energy out. And in order to go from that chemical energy to electricity, we have to transform that energy through a couple different types of energy along the way. And so we put in coal and we burn it, okay? And the burning produces heat, and we use that heat to vaporize water that is in a casing around our coal furnace or in pipes that run above and around our coal furnace. And so the water gets evaporated into steam by the heat from burning coal. That steam then is piped through narrower and narrower diameter pipes until it gets under high pressure. And then that steam is blown across a turbine. Okay, think about a big windmill or a propeller. It's got a whole bunch of blades on it, and they're spinning around and around and around. And the thing that's spinning those blades is the steam jet that was produced by burning coal. Okay, so now we've got this propeller turning. We've gone from chemical energy into kinetic energy. We're turning this turbine. That's still not electricity. Okay, but that turbine then is connected to a shaft that's connected to a magnet. Okay, and as the turbine turns, it turns the shaft, which turns the magnet. Right? And that magnet is in a big honking giant coil of wire. Okay, something like copper. That's has low resistance to electricity. And as that magnet is turned by the turbine, it flips north-south poles every time it turns. And so at one moment, the electrons in the wire are pulled towards the magnet, and in another moment, they're pushed away. And then they're pulled towards, and they're pushed away. And they're pulled towards, and they're pushed away. And all of a sudden, you have flowing electrons, which is electricity. That's how we go from coal to electricity. Okay? It's as simple and as complicated as that. At the end of the process, you will have as much electricity plus heat, plus smoke, plus water vapor, plus turning turbine and magnet and shaft, plus friction that you started with in the chemical bonds of the coal. Okay? But then the second law of thermodynamics comes into play. We don't lose total amount of energy every time we transfer from chemical to heat, from heat to kinetic, from kinetic to electromagnet. We don't lose total energy, but we lose energy quality. In every single transfer that happens, the quality of the energy degrades. Some of the energy that you start with is lost to the work that's able to be done by the system, to friction, to heat, to light production. And so only a fraction of the chemical energy that was stored in the coal ends up becoming electricity that's usable by us at the end. Because every time we make an energy transfer, we lose and bleed off a little bit of the high quality energy to those heat, friction, life sources. Okay. Is everybody with me? Okay. So we start out, the more energy you start out with, the more you potentially can have at the end. But every time you make a transfer in the system, you will lose some of your useful energy. And that's the second law of thermodynamics, which is that, it's very simply stated, the universe tends towards chaos, that in every single step, the quality of the energy degrades and goes down. There's always a little bit that's bled off. We talk about that energy as lost to the system, but I don't like to use that term here because I'm trying for you to visualize that what you start with is what you end with. And if we're losing something in your life, or to think out, it's still there in the total, it's not there for us to access to utilize. Okay. We can burn almost anything in that furnace to turn that turbine to run the generator to make electricity. Okay. The other thing that I want you to start to think about is that when we have hydro and solar energy, which makes solar together, we're going to be doing different processes in wind energy to turn that turbine without having to burn anything. Okay, but it's still the same electricity generation process. We're moving a turbine to run a generator. Okay, all right. So in terms of energy density, the more that you start with at the beginning, the more useful energy you will get out at the end. And it turns out that our energy resources vary in the amount of starting useful energy that we use. And this gives us our first kind of look at which of these resources is more profitable and which is more efficient and sustainable for their use. Okay, so if we imagine a 100-watt light bulb, which no one has a 100-watt light bulb these days anymore in their house, because we all are switched over to compact fluorescent or LED light bulbs, which use like 6 watts instead of 100 or something like that. But if you did have a 100-watt light bulb still in your house, if you burned a kilogram of coal, it would run that 100-watt light bulb for about 4 days. If you instead burned a kilogram of natural gas, it would run that light bulb for about 6 days. There's a little bit more high-quality energy in natural gas than in coal. If you instead used a wind turbine that ran for about a year, it could power that light bulb for 11 years. Just that 100-watt light. And if you instead started with a kilogram of uranium in your nuclear fission power plant, you could run that 100-watt light bulb for 140 years for yourself and your kids. Yeah, Taylor.
Does solar power turn a generator?
It does. And so usually what happens in our large solar thermal energy power plants is that we use high-powered light rays in order to evaporate water to run a turbine. The other thing that happens in photovoltaic cells is that we have a thin film of materials where a light photon activates them and produces an immediate flow of electrons to generate electricity. So in photovoltaic cells, we don't run a turbine. We start electrons moving just from the light photons themselves. There are different efficiencies, right? Photovoltaic cells, which is what we hear about most often, versus solar thermal.
Which one's more effective?
Definitely photovoltaic cells, because you can skip that whole step. Instead of every step you can skip in this process of going from your energy source to electricity saves you on that quality loss.
I was trying to say it's because everything is coming out with solar powered now.
Yes.
Like all the little devices are.
Right. And that's what we want. Okay, that's the next step. The only holdback is the production and the end of life of those solar photovoltaic cells. They're pretty nasty. And that there are rare earth elements that are utilized in their production. It's nasty chemical processes in order to produce them. And then when they're dead and gone, they're just as dangerous to the environment to waste. So
How long do they last?
it varies a lot. So like the little solar voltaic films that are on my kids' silly little bugs that dance then whenever they get little photons, that lasted about 3 days. In our big solar panels that we utilize for actual electricity generation, those should last somewhere on the order of 50 to 75 years with proper maintenance. They're built to last, even in the, bright full-on sunlight and the weather that they're gonna be exposed to. So it varies like the purpose and the quality of what you're starting with.
So what's the difference between that and like a calculator?
Your calculator film, I don't know what they utilize these days. It's been a really long time since I bought a solar calculator, although I have one. That solar strip is, I would say, medium between these two things.
Those things
And
last
that-
forever.
Right, exactly. It's another one of these thin films that's very lightweight, but it is much, much hardier and well built and durable than that little film that was on my kid's little solar powered bus toy. Okay, so just based upon how much energy there is to start with, we can see that there's a variety and there's a range of what's possible with our energy resources. Okay, coal is kind of at the bottom of the list. Biomass is down at the bottom of the list. At the top of the list definitely is nuclear energy. That is has the highest amount of energy available, and it's one of the most efficient in terms of transforming that nuclear energy, atomic energy, into electricity. Okay. Our second way of grading our energy resources is on energy efficiency, and there are two kind of competing ways in which to calculate energy efficiency for a resource. The first one is the one that our textbook utilizes to the greatest extent, and the one that is perhaps most familiar with us. Makes a lot of sense when we think about it from a business perspective or from a starting an addition, subtraction type of idea, and that's the idea of net energy. And net energy is this idea that you start with a certain amount of high quality energy, and it takes a certain amount of high quality energy to make the electricity or the transportation fuel that comes out at the end. And the net energy, the stuff that you get to sell on to the consumer as electricity or gasoline or jet fuel, is the net energy of the process. Okay, you're going to start with some amount of energy, but it's going to take you some energy to produce the saleable product. Okay, you have to take out the stuff that you have to use along the way, and that leaves you with your net energy at the end that you can move on. Overhead costs. Yeah, it's the exact idea of overhead costs. Okay, the way we calculate net energy is energy output. Okay, what you did at the end. Why do I have this that way? Yeah, it's okay. Okay, total energy output. Sorry, I'm thinking about it backwards. Total energy output, how much energy you're going to make at the end, minus the energy you had to put in to make that energy. Okay, energy output minus energy input. Okay, that leaves you with net energy that you can sell on. Okay. We're looking here at the diagram kind of the energy production of a power plant. Okay, it takes a little bit for that power plant, let's think about it again as coal or natural gas power plant. It takes a little bit to kick on, to start making energy. So at the beginning, all you're doing is adding energy in order to build the plant. It's not actually making any electricity. Then the plant starts producing electricity. That's the big blue triangle. Some of what it's producing it uses itself. That's the little yellow strip. And then after some period of time, you're using that power plant. The technology has moved on. Efficiency has changed. It's very polluting. You've lost your mineral resource in order to fuel it really easily and efficiently, so you're going to shut it down. And then there's a cost of energy to disassemble the plant and turn it back into wildlife habitat or a neighborhood, whatever you're going to do with that facility. Okay, and that's going to take energy again out after we're done producing electricity. Okay, so that plant has made a whole stack of energy, but we have to take out the energy it used to run itself, to build itself, to take care of itself at the end of life, and you're left with the net energy that it actually got to sell to consumers. Okay, that makes total sense. Again, the more energy you start with in terms of energy density that's there, the more potential energy, the more net energy you can get out at the end. The more efficient your process is, the less you have to use to run yourself and maintain yourself, the higher the net energy you'll have in the end to sell. Okay. The other way we think about energy efficiency is called energy return on investment, or EROI. This is energy return on investment. And it is, uses the same two terms, energy output, the energy you get out of the end, but instead of subtracting energy input, we divide it by energy input. It gives us a ratio of efficiency. To me, that makes a little more sense in terms of efficiency, that for every energy that you input, you get a certain amount of energy out at the end. Okay, it helps us normalize a little bit between different energy resources in comparison to net energy, but at the same time, it's less utilized kind of in the public media sphere to talk about ROI, because we have to think about ratios and somehow division is harder than subtraction. I don't know. Okay. We can then look at the net energy and energy return on investment of different energy resources. And this is a table from our textbook. And once again, tables can convey a tremendous amount of information in a compact form. That's why we use them. They're terrible for actually communicating information. So here we have a table from chapter 15 of our textbook. And it shows the net energy output minus input, of a variety of different resources for a variety of different purposes. Okay. What I want you to focus on is that for electricity production, which is the top corner here where I have some things highlighted in red, coal and natural gas have high to medium level net energy yields. They produce a useful amount of energy in that electricity generation process. Even though the energy density of nuclear is much higher than coal or natural gas, it has a lower net energy production. It takes a lot more energy to build and maintain and waste a nuclear power plant than a fossil fuel power plant. You'll also notice what I didn't highlight was that hydropower and wind have an even higher net energy yield than our fossil fuel resources when it comes to electricity generation. The other thing that I want you to notice is this bottom corner, which is about transportation. Our fossil fuel-based gasoline and potentially natural gas, methane burning, there are some actually methane burning engines out there, they have a pretty nice energy yield. They're pretty efficient when it comes to energy input versus energy output as a transportation energy resource. Diesel is medium to low. It depends where you get your gasoline from as to its energy efficiency, the net energy that's available. If you are able to just pump petroleum crude oil out of the ground, pretty high net energy. If you have to take it out of shale or tar sands, which I'm going to talk about in a second, the net energy available goes way down. It takes a lot more energy to process petroleum products from tar sands and shale oil than it does just to take it from a pool that's underground. The other thing to notice is that ethanol and biodiesel, which is one of the things that we want to turn to in terms of renewable energy resources for transportation, in today's manufacturing processes and distribution, have really low net energy yields. Okay, it is just above paying for itself. And this idea of net energy and energy return on investment is important because we have to have excess energy in order to run society. Okay, like that's what makes the process work. If the net energy or EROI that you get out of something is 1, okay, if you get out just enough to turn around and get more energy out of the ground, that means you're just generating enough electricity to run the power plant. It means that there's not electricity to send to the school or the bank or the government offices. Okay? You have to have net energy increasing output and increasing EROI, more and more positive EROI, in order to fuel our society and our civilization. We want to be utilizing energy resources that have a high net energy output, a very positive EROI, in order to provide for all the things that we want to do. Otherwise, it means that we're involved in the process of getting more energy. The lower the net energy, the lower the EROI, the more time and energy we utilize in just getting more energy to do electricity or transportation or communication processes. We're going to look at EROIs to a greater extent when we talk about renewable energies on Thursday, but this is the idea behind this type of energy efficiency. Our fossil fuels have those medium to high net energies for transportation and electricity in their particular sectors. But none of them really hold a candle to the net energy or EOI production of what we see in terms of renewables, particularly for electricity. And again, nuclear, this thing that has the greatest potential energy available to us, actually has a really low net energy and EROI production. It's really crummy when it comes to efficiency. Okay, is everybody with me?
Mhm.
Do you guys have questions at this point? Okay, I want to talk about sustainability now of these different fossil fuel products. Really quickly. Okay, we're gonna do it. All right, our first fossil fuel energy resource that we want to talk about is petroleum and natural gas. And we're going to talk about oil, we're going to talk about natural gas. We're going to talk about how they're made first, because they're made together. Does anybody know, other than for looking at the slide and you can use the slide, how do we make oil?
I don't know what that process is.
Yes, we're gonna refine petroleum, but how do we get the crude oil, the Texas gold that's bubbling up out of the ground?
We drill for it.
We drill for it. How did it get there? How did it get underground? Magic. It's not magic. Yeah, Willow. would you like to see? It does come from, it came from before the earliest stuff. Yeah, Caleb.
It's when dead plant and animal cells are underground, they compress and it turns to oil.
Right.
So it's ooze.
It's,
Nasty.
yeah, it's dead. In the case of oil and natural gas, it's largely marine plants and animals that have died. So organisms that live in the oceans. They died somewhere in the order of 1 billion to 500 million years ago. When their bodies fell to the seafloor, they started to be decomposed, and then they got covered over by sediment, and the decomposition process continued, and it turned anaerobic. And that process of anaerobic decomposition in the absence of oxygen produces certain products, certain organic molecules out of the end. Over millions of years, those organic molecules from that anaerobic microbial decomposition of marine organic matter, string all those things together, got heated up and got compressed, as Caleb said, in the Earth's crust, in the lower layers of the Earth's crust. And under high heat and pressure, that decayed organic matter turns into crude oil. If you subject it to even higher heat and higher temperatures and pressures, it turns into natural gas. And so often you find the two together in a particular mineral reserve. Of course, the gas is less dense, so it's usually at the top of whatever kind of cavern you have, and the petroleum is down at the bottom. These things are kept underground by layers of impermeable rock, so impermeable meaning nothing can penetrate through it, rock layers that are above them in the geologic strata. And so underground, you will have this pool then of this long dead and decayed organic matter that is then subjected to high heat pressure. It takes on the order of 300 to 650 million years for us to go from living marine organisms to natural gas and crude oil. And that is the replenishment rate process that we have a problem with in terms of our use of these particular products today. We're making them today. Marine organisms are dying and they're sinking, and this process is starting. But we are using them much faster than this decomposition and heat and pressure process is making new reserves of fossil fuels today. Okay, everybody with me? Today you learned how we make oil and natural gas. All right. In terms of petroleum, it is our #1 energy resource, and this is thinking about electricity and transportation combined. Okay, here in the United States, petroleum, crude oil, and its derivations provide for about 36% of our energy resources. Most of that is in the transportation sector. A smaller fraction of that is in electricity generation. We don't do a lot of just burning petroleum for electricity. And a little bit of it is in home heating and cooking processes. When we have these crude oil reserves underground, the way that we transform it from crude oil into electricity or transportation resources is that refining process that Rebecca mentioned. Okay, we're gonna pump this out of the ground, and we are going to send it to a refining plant. If you have been to the Gulf Coast of the United States, a lot of the shoreline where it's not nice beaches, where people are visiting and trying to have tourism business, is lined with these petroleum refineries where they pipe in this crude oil and they burn it. Okay, they subject it to high heat, and as it burns, different organic compounds evaporate off. And then they capture these different classes of molecules that burn off at different temperatures, and they let it condense into gas, gasoline, aviation fuel, heating oil, diesel fuel, grease, asphalt. Okay. As it gets hotter and hotter, different compounds come out, and we can utilize those organic compounds for different purposes. Yeah, sure.
So I was just thinking, you said that this oil and stuff sits in this impermeable rock. So
Yes.
nothing can get in, nothing can get out. Why
Pretty
is,
interesting.
why is that not where we put all of our crap?
So
You have
that
to
has
penetrate it to
been-
put it away.
Yeah, that's been an excellent question. So when we talk about sequestering carbon dioxide that's produced in these burning processes, either from our tailpipes or from these fossil fuel power plants, that is the most obvious place to put it, is to put it back in the ground where it came from, this carbon dioxide, whether it's gas or usually we want to liquefy it at that point, so that it has a better chance of staying there. That exact process is being tried in a couple different oil and natural gas fields in Australia and in Scandinavia. And thus far, it's worked pretty well. It looks like the carbon dioxide that they're pumping down there stays there, and it does spread out through the oil field, but it pretty much stays in that place. And it's not like it's just evaporating back up to the surface and returning to the atmosphere. That's our best chance for sequestration. It's difficult to pump our solid waste down there, which you could also think about doing, like using that as a landfill, simply because the wellheads are usually very small, and the junk that we have, like you can't shove a refrigerator down the wellhead. It just doesn't work. You can put solid waste down there, potentially. The thing to always consider in those processes is the energy input versus the savings that you get out. So it takes much more energy to pump solid waste down into these locations than to just dump it in the landfill. And so it's very much a convenience versus like cost profit kind of analysis. But you could potentially do that. You'd have the same problems in pumping solid waste down there as you would at a normal landfill, where now it's sequestered from the atmosphere. There's very little microbial degradation. It's going to sit there.
What is the rock?
Really varies.
Is it like, I feel like, to me, when I think of that, I think of like, is it like obsidian?
No, most of what's here on the continent is granite. And it really varies in the geologic location, exactly what you're going to find in these impenetrable layers above it. Some of it's shale, some of it's granite, some of it is more sedimentary rock layers that are going to be interspersed with these impermeable layers. Willow.
So if we're like utilizing this in the future and it's like, since you said it's green light,
Yeah.
so in the future is it only gonna be like underneath oceans that we're gonna be able to utilize this? Cause right now like on the surface like.
Yes and no. Right, so you can think that the process is going to start under the oceans, but remember these tectonic plates are moving around all the time. And so whatever gets entrained back onto the continental shelf. And that's another thing to consider is that the places where we find oil and natural gas reserves, like that's an indication that used to be covered by shallow sea in the past, which is interesting. Yeah, the entire Middle East, okay? Portions of the western United States. Okay, we have tons and tons of reserves both here in the United States and globally in terms of petroleum and natural gas. This is looking again at petroleum. The big green dots are where we have proven reserves. I think they've been kind of tapped, or like we've noticed that they're there, but we aren't always utilizing these particular resources. I think we're familiar with Texas, California, Alaska being big places where we have petroleum reserves. Depending upon what exactly we are thinking of as a petroleum reserve, the western United States actually holds a tremendous amount of this really valuable resource. Our current interest in this is what's available in the Arctic. The Arctic is a relatively shallow ocean basin, And so it's interesting to think about what might be just offshore of Alaska in terms of the continental shelf there. And then what is available, of course, in deep ocean drilling, where there's most of the planet's surface and that type of landscape and environment. What types of oil reserves are hidden in those locations? Yeah, Caleb.
So it says there's 36, well, first of all, what is mean total?
I think mean total means the billions of barrels of oil that we think are out there to be gotten in the unicontinental and Alaska, United States.
Okay, so that's what they're,
Yeah, there's like 36,000 billion barrels of oil.
what is in a barrel?
I think, I can't remember if it's, I always envision the barrel as like a 50-gallon drum.
Yeah,
Big
yeah.
drum of things. I have to look if that's actually true, if it's 100 gallons, kind of like 100 liters, 100 gallons.
It just seems like some of these graphs, man, I need to like.
Oh, yeah. They make nice, like, oh, look, this is where they are, and the size of the blob gives you an idea. There's more in Montana, in the Dakotas than there is in some place like Nebraska. Like, that's the general idea. How much that actually means. Right.
36 billion barrels of oil.
Yeah, like, we're not gonna run out of these fuels, even at our current use rate, for many, many generations.
42 gallons.
Oh, 42 gallons in a barrel. So it's close to that 52 gallon barrel. When we use petroleum for energy resource, mostly in transportation again, as a medium EROI and net energy, it's fairly efficient. Our pumping of it is relatively low on the habitat destruction scale. Okay, like you don't need a big area to set up a wellhead to pump this stuff out. And we have a very efficient distribution system. It's really easy for us to take petroleum for where it is pumped to the refinery and then spread it out all over the United States to all of the gas stations and all of the power plants that want to utilize it. This is a system and an infrastructure that is already set up. Those are things that are difficult and are hurdles for things like biodiesel that are really problematic when we think about solar and wind generation in terms of electricity, or even for electricity regeneration of electric cars when we think about batteries. I have a whole infrastructure that has to be built in order to distribute that energy, and that's already in place for these types of fossil fuels, largely because this is what we started with. Okay, so there are good things about petroleum, is what I'm trying to say. There's a lot of it, it's readily available, we know how to work with it. It has a pretty decent energy. There are two resources of petroleum other than just bumping it out of liquid deposits underground. And the first one of those other ways of getting petroleum out of the geologic layers is shale oil. And you may remember when we had our little geology day, one of the minerals I had to interact with was shale oil, and oil shale in particular. And this is usually a very black rock like this. If you were to touch it, it would feel very oily like soap. Because it has a tremendous amount of petroleum locked in between the individual mineral molecules of the shale rock. And when you squeeze that rock piece, and you subject it to some chemicals and a little bit of heat, you squeeze out crude oil. Yay, more. Okay, yeah, well, how much crude oil? Depends on the rock. Some of it contains more, some of it contains less. It's kind of like high and low grade ores. Some of these oil shales contain a lot of petroleum in them. Some can have relatively little. And of course, when we then are interested in mining and processing these resources for oil production, we're going to use the high concentrated shale oil first, and then we're going to move to the low ones. Okay. We have a tremendous amount of oil shale in the western United States. We have about 72% of the known global reserve. Kind of like the other 30% is in the provinces of Canada, just adjacent to places like Montana and Idaho. This means that this is a potential way for us to become energy independent when it comes to petroleum products and gasoline, if we want to be doing all of this production and use on our own here in the United States. The other way that we can get petroleum out of the ground is through tar sands. And we don't have a tremendous amount of tar sands here in the United States, but there are big landscapes.
Not Tarzan.
Yeah, not tar sands, tar sands. two words. There are big reserves of this in Canada, and again, shale oil and tar sands are very attractive to the Western world because it's a way to not be dependent upon the Middle East and Europe and Russia for our petroleum products. Okay. In the case of tar sands, you essentially have sand, okay, and it has bitumen, which is a coal-like product in it. And when you put high pressure water and heat onto this sand, you can liquefy out the coal and it becomes crude oil. Okay. It is a very energy intensive process to get crude oil out of shale or tar sands. Okay. Both of these products, remember, have a low net energy. They are very energy inefficient. It takes a tremendous amount of energy input in order to get out useful crude oil at the end of the process. This means that we have not been doing a lot of shale or tar sand mining and oil production from them until really, really recently when the price of oil went up to like $100, $117 per barrel. Then there was enough production to pay for this processing. With the drop back down of oil prices, places that are doing shale oil and tar sand production for crude oil have started to decline in the last decade because there's not enough money to be made in the process because it's so energy and cost intensive in the first place. This is the problem with mining and oil production in the Dakotas today. It was boom town, late 1990s, early 2000s, and now those places are ghost towns because the price of oil has dropped and these processes don't pay for themselves.
Do a two-in-one.
Do what?
Do a two-in-one. You got sand and you got tar. You make the energy, you make the glass.
Yes, exactly. And that's again what's attractive about the tar sands. Most of the current tar sand manufacturing and processing is done in Alberta in Canada. And that particular province is like 50-50. Part of them are like, yes, let's make money, let's do this is our natural resource, let's use it. The other 50% of them are like, this is an environmental catastrophe. Okay, and it totally is. Which is like the dark side of this, both for shale and tar sands I haven't talked about. And so Alberta has been really back and forth about utilizing this area. When the price of oil went up, they kind of went in for it, and again they backed off again because they have all these environmental problems that come out at the end. And now that gasoline is less expensive, it doesn't make money for them as a problem. Okay, all right. So our problems with petroleum, and the big problem with petroleum use is the waste that it produces. And there are kind of 6 categories of waste or pollution that come out of using petroleum. And the first is carbon dioxide. When we burn petroleum, either for transportation energy or for electricity generation, we generate carbon dioxide. It's one of the products that's given off when we break the chemical bonds in the organic matter that's present. So we get a tremendous amount of carbon dioxide out. It is not the worst in terms of fossil fuels for carbon dioxide production, but it is in the middle of the pack. Okay, so one of the problems is that when we burn this particular petroleum, we make carbon dioxide. The next problem we have is that a variety of different types of pollutants are made. And this comes in its very base form when we have oil spills and leaks of pipelines or in facilities or at wellheads. When we have tankers that spill, then we get petroleum that's on the ground or in the water, and we're familiar with the consequences of that type of oil pollution. In particularly the manufacturing process for shale oil and tar sands, there's a whole suite of chemicals that are utilized in order to purify the oil from the thing that it started out in. And when those mining chemicals leak, or when they have to be disposed of in holding ponds, they become potential pollutants. And when those things spill, then we have a chemical pollution that's out in the environment. The next problem with burning petroleum products is that when we burn it, we don't only get off carbon dioxide molecules, we very often get off other molecules, which are themselves pollutants that can be harmful for human health, and are themselves potent greenhouse gases. They too can absorb heat in the upper atmosphere of the Earth and cause us to retain heat on a global scale. And in particular, we do get off methane, which is natural gas. And another big problem that we have when we burn petroleum products is we get off sulfur dioxide. We get off There's a whole suite of these sulfur compounds that we're gonna identify as air pollutants, and sulfur dioxide is one that comes when we burn gasoline. The other kind of waste and pollution problem that comes with petroleum use is in the extraction procedure. We've talked all about mining. We have the same problems when it comes to environmental hazards, when it comes to economic hazards, when it comes to human health and minor hazards, worker hazards, when we're mining petroleum as when we are pulling out diamonds, or coal, as we're going to talk about. Okay. The extraction process itself is inherently dangerous and is inherently polluting as well. All right. The fifth one here is that these things can have a low net energy, particularly in terms of the shale oil and our tar sands. Those products have an EROI of just around 5. You remember we kind of look at our EROI pyramid, okay? We want EROIs that are like 10 and 15 if we want to do things like have schools and a functioning government and arts and crafts, okay, in our neighborhoods and in our townships. The low EROI of these two particular ways of getting petroleum really influences whether or not they're useful to us as a society. And the final thing to consider with petroleum is that it uses a lot of water, uses a tremendous amount of fresh water, particularly in order to push out heavy oil. I didn't talk about this today, but crude oil comes in a bunch of different densities, and there's light crude oil and there's heavy crude oil, and they're utilized best for different purposes. If you want to move that really dense stuff out of the ground, you have to push something else in order to force it out many times. So we do that with fresh water. That's the easiest, most successful resource. And so it uses a lot of fresh water to do that. We're going to talk about fracking as it relates to natural gas production in just a second. But at the same time that we're using fracking liquids and fresh water that they're dissolved in order to push out natural gas in our oil fields, we can do that to push out the remaining oil fields. And so we end up potentially with a lot of fresh water that goes into energy production when we utilize petroleum. Philip.
Or do they use like sandy
Salt water.
Yeah.
Sally, great idea. Okay. Usually they use what's right next to them as a lake
They
or
can
a
use the
stream, which
polluted
is the fresh
water.
water that we would like to use for water for irrigation purposes too. I think it would be wise if they started using gray water or water from sewage treatment plants for this purpose. Salt water is not a great option because it damages the equipment and it leads to corrosion. And then we're pumping salt water into potentially arable land. That's like way worse, right? If we suddenly have fresh water and then it gets polluted with salt water that we pumped underground. Yeah, that's just definitely more salt water. It could work, but the consequences are really obvious if we had a problem versus just putting it fresh. Okay, so petroleum is good. We know how we make it. We know where it's useful. We have a lot of it. We have a lot of it here in the United States, but there's a suite of problems that go along with it. And again, we're going to kind of highlight and save the carbon dioxide problem as our most dramatic problem with utilizing petroleum products because it does relate to global climate. All right, I just have a couple slides on natural gas. Natural gas, again, is made alongside petroleum products. It's from those dead and decaying marine organisms that have been subjected to high heat and pressure. Natural gas is methane. It is CH4. It's flammable, which means that you can burn it and create heat for heating your house. You can burn it and create heat for cooking. You can burn it and you can use the heat generated to make electricity. It does the same thing as if you burn coal in a coal power plant. That heat goes through the same process. In our natural gas reserves, usually between 50 and 90% of the gas that is there underground is actual methane, which is the flammable part. There's always some other gases in there too, like butane and propane, to a lesser extent, hydrogen sulfide. So usually when we refer to natural gas, and especially refined natural gas that you're going to be utilizing in your home, that's methane, that's CH4. All right, it provides for about 28% of our global and U.S. energy needs, and again, it like petroleum, kind of runs across the board in terms of what it's useful for. We definitely see natural gas, I think, as a more diverse product on the market. It so easily lends itself to being utilized for cooking and heating as well as electricity generation, that we see it in all three of those really big sectors. We don't do a lot of it in transportation yet, but again, it is one of those potential stepping stones from petroleum into something that's more renewable. Okay. As I mentioned, it's mined alongside petroleum products. Usually what happens is that we liquefy the natural gas so that it is easier to pipe and move through our existing transportation system for petroleum products to the refineries and then out for distribution. We do that by putting it under high pressure. And that usually generates then liquefied natural gas, or LNG, which is the product that we consider oftentimes in terms of selling to China to help them replace their coal-fired power plants. Like petroleum, we have big U.S. and global reserves of natural gas. Like petroleum products, it has a medium net energy and EROI. That's pretty standard. It's definitely becoming more and more of a market share, particularly for electricity generation. And it's very attractive to our energy resource use because it produces 30% less carbon dioxide than burning petroleum products and 50% less carbon dioxide than burning coal. And so that is a huge savings when it comes to waste production in terms of carbon dioxide compared to our other types of fossil fuels for energy generation. Okay, so it's better, but we do have some real concerns, just like for petroleum products when we utilize natural gas. A big one today is a variety of concerns related to the fracking process. So fracking is utilized to pump more natural gas out of a given geologic field, a given reserve field. In the fracking process, we put high pressure water with a variety of solvents and chemicals in it underground in order to push the natural gas and leftover petroleum products out of the little seams and little rock crevices that are present in the geologic layers. It also means that by pushing stuff into the rock layers, we can push natural gas out of fields where it's not collected in an underground cavern or a little pocket. It means we can get all these little tiny bubbles out that might be very distributed within a region. And so fracking really helps us increase the amount of natural gas that we can get out of a particular region. It has opened up a wide range of different regions to natural gas production that weren't available to us before. We were just doing kind of drilling and wellheads. Okay. So it's good for natural gas production, but fracking has a ton of environmental concerns related with it. Like, what happens to that fracking liquid after it gets in the ground? Where does it go? Does it stay there? Does it interact with organisms? Does it get in our drinking water? When you are pumping out the natural gas, you get out this slurry of stuff that includes the natural gas that you want, as well as all these little sediment particles in your fracking liquid. What do you do with that slurry of stuff? Where do you put it? It's waste. It's not useful. How are we going to clean that up? Is it toxic? We don't know. This is the first time we started to use lots of these chemicals. For communities that live next door to fracking operations, they do often find that they have higher carcinogen-containing compound concentrations in their drinking water. In the case here of this woman living in Pennsylvania, her tap water now is flammable because of fracking. Fracking can cause earthquakes in areas that are not accustomed to them. And then when earthquakes happen, things like underground aquifers burst and floods happen in strange places and ways. And these fracking liquids get released into communities. there can be very detrimental downstream consequences as the fracking process. Yeah,
Right.
you get to buy bottled water. Yay.
You don't put fires out in water. That's
So,
what you
yeah,
don't
you
do.
don't get to put out fire. This is what you get to try to sue the agency, the business entity that's doing the fracking to remediate what they have to do with it. I don't think so.
I don't know how I feel
For
about
a hot second, if you're a pyro, and then you get thirsty.
When we use liquefied natural gas as our starting resource, there's a lower net energy and ERI associated with that because it takes a lot of energy to liquefy natural gas. Again, that idea of energy input versus energy output. Every time we have to do something to make this product useful, it takes energy to do that. And so it takes out of what's available to us at the end. The liquefied natural gas, again, is attractive because it's an easy transportation towards of moving natural gas from where it is found to where it is actually utilized. You can utilize the same pipes again as our oil reserves. One thing that is concerning about natural gas is that it is lower cost, which is great when it's competing against coal and petroleum. It is bad when it's competing against renewable energy resources. It means that because natural gas is cheap, we're going to keep using it. We're going to keep polluting with it in terms of climate change in comparison to switching to full-on renewables. Okay, and that's the last item here, is that there is an aspect of climate change to utilizing natural gas. We do get some carbon dioxide out, even though it's the best of these fossil fuels for carbon dioxide production. And it's methane itself. Okay, if it leaks or gets into the atmosphere, you don't burn all of it. It's uber bad. Okay, a molecule of methane absorbs significantly more heat in the atmosphere than a molecule of carbon dioxide. So it in itself is a potent greenhouse gas. Okay, any questions about natural gas or petroleum? We use them because they are useful, they're readily available to us, we have the infrastructure and the knowledge of how to use them. We're just starting to deal with the consequences of long-term use.
So if I can frack my backyard, will it?
Not quite.
Are you gonna go home and light a match by your faucet?
You might.
You'll have to report back to Miss Andrew.
I think I'll be the one who's
Well, I mean, my kids went to this camp yesterday at Cincinnati Museum Center, and all they came home with was a litany of fart jokes from the other campers.
Oh.
A litany
In what?
of fart jokes. Litany of fart jokes.
Right.
Like, there's value in that, of like interacting with your peers.
But can we have some variety?
I don't want fart jokes, that's all. Okay, let's talk about coal and nuclear energy here at the end of class. Coal is produced from decaying plant matter. So in natural gas and petroleum production, we had animals and plants that can participate in the process, but it's only plant matter that can be transformed into coal at the end of the process. And most of the time, this is terrestrial plant matter that's going to become coal. It's less influenced by the marine environment, and a lot of the plant matter that is capable of becoming coal is found in kind of swampy, boggy areas. That's the place where the anaerobic decomposition process is most likely to happen. It's the same process that produces coal as natural gas and petroleum products, but you start with something different, you will get something different at the end. Okay, so we're starting with terrestrial plant matter. We're subjecting it to anaerobic degradation and high heat and pressure in the Earth's crust. We will get coal out at the end. You will get this solidified organic matter that you can then burn again to produce heat and energy. Mostly, again, we utilize coal for in heating, electricity generation, and lots of people around the world still burn coal as their main cooking energy resource. It takes 300 to 400 million years for dead and decaying plants to become coal reserves underground. Places that had forests and were the first kind of grasslands that, again, the dinosaurs kind of interacted with, that's the coal that we're seeing available to us today. It takes about 10 feet of plant matter to make one kind of cubic foot of coal. Okay, so there's you have to start with a lot of material before you're going to get something out that's useful at the end. Just like there are grades of crude oil in the ground, there are grades of coal. You can burn peat, which is the start of this process, definitely for energy production. Anthracite is the low sulfur, clean coal that we hear so much about today in the coal industry. But you can burn any of the kind of in-between stages. All right. It is our most abundant fossil fuel resource. Coal provides for about 40% of global electricity. That's generally the biggest sector where it is utilized as an energy resource, is in coal-fired power plants for electricity generation, like we saw our diagram talking about energy density and energy efficiency. Here in the United States, it provides for about 33% of our electricity. Here in the U.S., we can see from this graph from our textbook, our use of coal is slowly starting to tick down. And electricity plants that have been burning coal in the past are increasingly turning to burning natural gas. Natural gas is cheaper for them, and it comes with fewer environmental regulations and stipulations in order to utilize it. But China's use of coal has increased almost exponentially in the last 25 to 30 years or so. And that's where we see the largest growth of this sector. The use of coal has really been the power resource behind China's industrialization. And again, remember that all of those things that China is making and manufacturing with coal, they sell to us. So that even though we're not using coal here, we've kind of transferred that coal use to other countries. Like other fossil fuels, it has a medium to high net energy and EROI. And as I was talking with Caleb earlier in class, we do currently have carbon capture technologies in place where we can capture the CO2 that's produced from burning coal. We can capture it, we can clean it up. What we do with that carbon dioxide and how we sequester it and keep it from returning to the atmosphere is the big question. And that's why we don't see a lot of carbon capture and sequestration done today, because we're definitely still in the experimental phase. Okay. The problems with coal really come in three areas. The biggest problem with burning coal is the vast amount of carbon dioxide that it produces. Just a tremendous amount of CO2 is given off by burning this organic material. Much more than petroleum and much more than natural gas. And that makes it one of the greatest contributors to climate change that we are experiencing. When we burn coal, there's a whole bunch of particulates that come out in the process. And those things can cause cancer. They contribute to asthma. The sulfur in it adds to acid rain production, which we now have a suite of sulfur scrubbers on most coal-fired power plant smokestacks, and we have reduced acid rain and acid kind of sulfur pollution in that way. A big problem that's left over too, as you're done burning the coal, is you're left with this ash, this stuff that did not burn completely. And a lot of that contains dangerous heavy metals that then have to be wasted in the appropriate fashion. We are familiar already that the coal mining process is a leading contributor to habitat destruction and land and water pollution in the mining process, as well as in the manufacturing process to get the coal over to the power plant. Coal was the first thing, right? When we started doing engines and electricity generations, we burned coal in them because that's what was, honest to God, laying on the ground in Great Britain where these guys did this, okay? And so it has been our traditional energy resource, but our use of it for the last 175 years has produced tremendous problems, most particularly when it comes to pollution and when it comes to carbon dioxide. All right, my next slide just reminds you of some of that habitat and the dangers that come along with coal mining in the first place. And this is what I want you again to remember with each of these energy resources, is that there is a cost to their production and there is a cost to their use. When you think about this life cycle analysis of these different energy resources. Okay, where am I on time?
It's probably 5 minutes.
All right. Let's talk about nuclear energy very quickly, and I may introduce to you the idea of it and kind of how we use it. problems associated with it in Thursday. Nuclear energy is our last non-renewable energy resource. It is not a classic fossil fuel, and we have a tremendous supply of this. We're not in any danger of running out of our nuclear energy resources, but it is not replenished. What we have in terms of uranium and plutonium resources for this energy production is what we have. It does not short circuit the global carbon cycle like our fossil fuels do. Burning it does not in general produce a ton of carbon dioxide, although there is some CO2 in the process of mining and refining these radioactive materials and in maintaining and closing down the plants. There is some CO2 generation, even though the exact process itself does not generate CO2. Okay? What we're doing in our nuclear energy production is nuclear fission, and that means that we have atoms that are splitting apart. And when these radioactive atoms split apart, they release heat, which we immediately use to vaporize water into steam, turns turbine, runs a generator, makes electricity. Okay. And another thing that's given off by these atoms when they split is a particle. And that particle knocks into another atom and causes it to split and give off heat. And a particle that then goes on and hits another atom and splits. And so you get this chain reaction of energy production when we start the process of nuclear fission. In order for this to be productive in terms of heat production, to turn into electricity, we have to concentrate vastly these radioactive atoms into fuel rods, usually that are utilized. And so there's a big mining aspect to this and the detrimental aspect of mining. There's a whole concentration procedure in order to make something like uranium yellowcake, right? That's then useful in nuclear fission, both for energy production as well as for nuclear weapons.
So it's like an atomic bomb going off.
Oh yeah, very much so. A controlled atomic bomb. And that is the absolute key. Okay? Like, honestly.
They've had meltdowns before.
Oh yes, they have. So,
Sure.
you may be familiar with Chernobyl, which was an actual full core breach of a nuclear power plant in Russia. And on 3 Mile Island, they had an almost breach, and they had to dump cement on their nuclear fissile material in order to stop the nuclear fission process in New York.
Yeah.
Okay. In terms of usefulness, in the nuclear energy production, there's actually very low environmental impact, and there's not a lot of risk of exposure to radioactive materials to the environment or humans in the process. Like, we know how to do this relatively safely. Yes, there are accidents. But in terms of how many times we do this each day, it's very safe. So it's low risk. There are almost no carbon dioxide emissions, very low CO2 emissions, and it has a high energy density. We can make a tremendous amount of energy in terms of electricity on site by allowing nuclear fission to take place in these reactors. The problem, though, is that we spend a lot of electricity to mine and concentrate radioactive materials, to clean up these facilities when we're done using them, and to transport that electricity to useful purposes. And that impacts the overall net energy ROI of nuclear. When nuclear energy came onto the stage in the 1950s, 1960s, it was seen as the solution to fossil fuels. Because here we were going away from almost all of the problems associated with fossil fuels. It gave us a new suite of problems, though. Okay? It is the waste generation is so problematic because it is so hazardous to ourselves and the environment that it has almost negated the great aspects of nuclear energy as a resource. Okay, and so that's the last slide for today, is to think about the unappealing aspects of nuclear energy. And the worst thing about it is the radioactive solid waste that it generates. That stuff sticks with us for literally billions of years. Okay, and we don't know how to deal with it in the interim safely. Okay. The other big risk, of course, that's associated with nuclear is the accidents. When we have these leaks, we had the Fukushima, that accidental nuclear release that happened in association with the earthquakes and the tidal waves off Japan a couple years ago. That's the most recent one. Talk about Chernobyl. This is a picture of 3 Mile Island facility. It was really cool. It's cool in that, like, it's cool, but terrible.
it's like train wreck.
Yeah, yes, like trainer. The other thing that's really, really problematic, I would say, about nuclear is that in the energy production process, we're making the same material that we utilize in nuclear weapons. And so that means that there's a huge safety aspect to all of this technology and energy production associated with nuclear. That we have to have high safety standards for these facilities to make sure that that radioactive material is utilized to make electricity and not utilized to make bombs. Okay, this is where we'll pick up. This is a slide that we'll start with in the beginning of class on Thursday. As you are leaving today, I want to thank you for eating popcorn. If you would like more popcorn, I have another bag of popcorn. We're going to be in at chapter 15, renewable energy, on Thursday. And your next homework assignment is homework 5. Okay? And that is online as well as here if you would like to work. Okay, thank you.